Aero Engineering Thermodynamics. The Carnot principles. The second law of thermodynamics puts limits on the operation of cyclic devices as expressed by the Kelvin-Planck and Clausius statements. The heat engine cannot operate by exchanging heat with a single reservoir, and a refrigerator cannot operate without a net energy input from an external source. Two conclusions pertain to the thermal efficiency of reversible and irreversible, i.e., actual heat engines, and they are known as the Carnot principles. Figure expressed as follows. 1. The efficiency of an irreversible heat engine is always less than the efficiency of the reversible one operating between the same two reservoirs. 2. The efficiencies of all reversible heat engines operating between the same two reservoirs are the same. To prove the first statement, consider two heat engines operating between the same reservoirs, as shown in Fig. One engine is reversible and the other is irreversible. Now each engine is supplied with the same amount of heat QH. The amount of work produced by the reversible heat engine is REV, and the amount produced by the irreversible one is WREV. In violation of the first Carnot principle, we assume that the irreversible heat engine is more efficient than the reversible one, that is, TH of TH and thus delivers more work than the reversible one. Now let the reversible heat engine be reversed and operate as a refrigerator. This refrigerator will receive the work input of REV and reject heat to the high temperature reservoir. Since the refrigerator is rejecting heat in the amount of QH to the high temperature reservoir and the irreversible heat engine is receiving the same amount of heat from this reservoir, the net heat exchange for this reservoir is zero. Thus, it could be eliminated by having the refrigerator discharge QH directly into the irreversible heat engine. Now considering the refrigerator and the irreversible engine together, we have an engine that produces a net work in the amount of WREV while exchanging heat with a single reservoir, a violation of the Kelvin-Planck statement of the second law. Therefore, our initial assumption that TH of THREV is incorrect. Then we conclude that no heat engine can be more efficient than a reversible heat engine operating between the same reservoirs. The second Carnot principle can also be proved in a similar manner. Replace the irreversible engine by another reversible engine that is more efficient and thus delivers more work than the first reversible engine. By following through the same reasoning, we end up having an engine that produces a net amount of work while exchanging heat with a single reservoir, which is a violation of the second law. Therefore, we conclude that no reversible heat engine can be more efficient than a reversible one operating between the same two reservoirs, regardless of how the cycle is completed or the kind of working fluid used. The thermodynamic temperature scale. The temperature scale that is independent of the properties of the substances that are used to measure temperature is called a thermodynamic temperature scale. The hypothetical heat engine that operates on the reversible Carnot cycle is called the Carnot heat engine. The thermal efficiency of any heat engine, reversible or irreversible, thermal efficiency is equal to 1 minus QL/QH, where QH is heat transferred to the heat engine from a high temperature reservoir at TH, and QL is heat rejected to a low temperature reservoir at EL. For reversible heat engines, the heat transfer ratio in the above relation can be replaced by the ratio of the absolute temperatures of the two reservoirs. Then the efficiency of a Carnot engine, for any reversible heat engine, becomes efficiency of Carnot engine is equal to 1 minus TL/TH. This relation is often referred to as the Carnot efficiency, since the Carnot heat engine is the best known reversible engine. This is the highest efficiency the heat engine operating between the two thermal energy reservoirs at temperatures TL and TH can have. The thermal efficiencies of actual and reversible heat engines operating between the same temperature limits compare as follows. No heat engine can have a higher efficiency than a reversible heat engine operating between the same high and low temperature reservoirs. Most work-producing devices heat engines in operation today have efficiencies under 40%, which appear low relative to 100%. However, when the performance of actual heat engines is assessed, The efficiencies should not be compared to 100%. Instead, they should be compared to the efficiency of a reversible heat engine operating between the same temperature limits, because this is the true theoretical upper limit for the efficiency, not 100%. The maximum efficiency of a steam power plant operating between TH equals 1000 K and TL equals 300 K is 70%. The CARNOT refrigerator and heat pump. The refrigerator or heat pump that operates on the reversed CARNOT cycle is called a CARNOT refrigerator, or a CARNOT heat pump. The coefficient of performance of any refrigerator or heat pump, reversible or irreversible, where QL is the amount of heat absorbed from the low temperature medium and QH is the amount of heat rejected to the high temperature medium. The COPs of all reversible refrigerators or heat pumps can be determined by replacing the heat transfer ratios in the above relations by the ratios of the absolute temperatures of the high and low temperature reservoirs. Then the COP relations for reversible refrigerators and heat pumps become: these are the highest coefficients of performance that a refrigerator or a heat pump operating between the temperature limits of TL and TH can have. All actual refrigerators or heat pumps operating between these temperature limits TL and TH have lower coefficients of performance. No refrigerator can have a higher COP than a reversible refrigerator operating between the same temperature limits. The coefficients of performance of actual and reversible refrigerators operating between the same temperature limits can be compared as follows. The COP of a reversible refrigerator or heat pump is the maximum theoretical value for the specified temperature limits.